Welcome to Empowered Learning. This video will be about performing integration on functions that either have an exponential or logarithm in it, or when we take the antiderivative of a function that's in our integrand, it will end up either having an exponential or a logarithm as part of the antiderivative. So we're going to do several examples here. And of course, working with these types of integrals here, there are some things that we need to watch out for in dealing with, our antiderivatives for like 1 over x, like in this first example here, which will be natural log of absolute value of x. So we need to make sure that we put the absolute value part in there and check that out. But other than that, we just want to get very comfortable with doing integration for these types of situations here. So let's go ahead and get started with this first example. So we want to evaluate the definite integral of, let's say, 1 over x dx, and we want to evaluate that from -3 to -2. So the first thing that we want to realize here before we even get started is that we are looking at this function 1 over x. And of course, 1 over x, if we draw it, kind of looks like this. Okay. And of course, we know we have a vertical asymptote here at x equals 0. But conceptually, we are wanting to find the area under the curve of this particular function here from x equals -3 to say about right here to x equals -2. So we want to find this area under the curve here. Okay. So in doing that, the first thing that we realize is that the antiderivative of 1 over x dx, and I'm saying that because we could look at this like that, is going to be the natural log of absolute value of x. So we'll go ahead and rewrite this here. 1 over x dx. And the antiderivative of that is natural log of absolute value of x, and we will evaluate that from -3 to -2. And of course, -3 is smaller than -2, so that's why that goes on the bottom and -2 goes on top. So if we come here and evaluate it, we will put natural log of absolute value of -2 minus natural log of absolute value of -3. And of course, the absolute value of -2 is 2, so this just ends up being natural log of 2 minus natural log of 3, and we could keep the answer that way, or we could just rewrite it as natural log of 2/3. Using our logarithm property, it says that the difference of logarithms is the same as doing log of the quotient of those two things. So basically this law here. So it's a log A, log B, and let's say we have some base Z there, then this could be rewritten as log base Z of A divided by B. Okay. All right, and so that is our answer to our first example. So let's move on to the second one. So for our second example, we see that we want to take the indefinite integral of this rational function here. And the main thing that we're going to see is that we could use the substitution rule here to rewrite this indefinite integral. And in doing that, we're going to see that our integrand is going to look something similar to what we had in example 1. So if we go ahead and start this, let's go ahead and pull that 8 out of the integral and just rewrite everything else. And so now let's let u equal y raised to the 8th minus 13. And that's going to imply here that du over dy is going to be equal to 8y raised to the 7. And of course, the derivative of any constant is 0. And thus, if we have 1/8 du, just basically rearranging this around here, this is going to be, I'm running out of room here, so let's move this. So basically, we're going to rewrite this, and 1/8 du is going to be equal to y raised to the 7 dy. Okay, so we got du over 8 is going to be equal to y raised to the 7 dy. And of course, that's exactly what we want to replace. So this will be replaced with 1/8 du, and our denominator here will just be replaced with u. Okay, so therefore, let me switch back colors again here. So therefore, what we originally had here, 8 integral, let's fix that integral sign. All right, so 8 integral of y raised to the 7 dy over y raised to the 8 minus 13. That's just going to be 8 integral of, 1/8 du all over u. And of course, our 1/8 times 8 will just equal 1. So we essentially just have the integral of du over u, which is the same as the integral of 1 over u du. And we know that the antiderivative of 1 over u is just going to be natural log of absolute value of u plus our integration constant, since we're dealing with an indefinite interval versus definite interval. And here we go ahead and substitute back what u is. And u is going to be y raised to the 8 minus 13 plus c. And so notice here that we need to have the absolute value signs on there, because our function y raised to the 8 minus 13, and I'll just draw it like this to kind of make my point. So let's say if we have a function x in terms of y here, well, y raised to the 8 minus 13 is going to look something like this. And notice that there are values, mainly speaking from this point here to this point here. For all these values of y, the y raised to the 8 minus 13 is negative. And of course, we know we can't take the natural log of negative numbers. So the only way that we could do that is if we were to have the absolute value signs here to make this work. And so that's part of the reason why we need them there. Okay. All right, so let's move on to our next example. All right, so in this next example, it's going to be pretty much like example number 2. We need to find out what it is that we want to use substitution on. And we know that we're going to use substitution because if we look at this integrand straight up, we know that, hey, we're not going to be able to just look at this and say the antiderivative is this. But we do see here that if I was to allow my denominator here to equal u, then of course, if I took the derivative of it, I know that the derivative of any constant is 0. And ignoring this 5 here, if I take the derivative of tangent, that's going to be secant squared. And I see that I have that in my problem here. So that lets me know that, hey, substitution would actually work well. So here we're going to say let u equal 2 plus 5 times tangent of 2t. And if that's the case, then we know that du over dt is going to be equal to 5 times secant squared of 2t. And since this is a composition function, we have to take the derivative of the inside function. And the derivative of 2t is just 2. And so this would just end up being 10 secant squared 2t. Therefore, what we would have here is that du is just equal to 10 secant squared. Whoa. Don't know what happened there. So let's see, secant squared of 2t dt. And of course, that is exactly what we have up here. Okay, so all of that just ends up being, du, not dt. So therefore, we'll go ahead and switch colors for this one. So therefore, what we have is this 10 secant squared of 2t dt all over 2 plus 5 tangent of 2t. That simply just can be rewritten as du over u. Okay. And of course, again, the antiderivative of 1 over u times du is just going to be the natural log of absolute value of u plus our integration constant. And we know that u is actually 2 plus 5 times tangent of 2t. So 2 plus 5 times tangent of 2t plus c. And that ends up being our final answer there. All right, so let's move to the next example. So for our next example here, and actually this should be a parenthesis right there, but for our next example, we see that our integrand is actually an exponential function. It's actually a composition function where the outside function is an exponential. So here, again, technically we would be doing substitution here, but it's really not necessary to go through those steps there. And I say that because we know that the antiderivative of e raised to the 1/2 x, the antiderivative of that in general is just going to be e raised to the 1/2 x divided by 1/2 here, which is the same as saying 2 times e raised to the 1/2 x. Okay. Now, we know that because, of course, if I was to actually take the derivative of 2 times e raised to the 1/2 x, then of course the derivative of this, and I'll just write it out. So the derivative of that would just be 2 times 1/2 e raised to the 1/2 x. And of course those 2's would reduce to 1 and we would get what we start with. Okay. So because of that, we already know what the antiderivative of this is straight up. So that's really not the issue. What we need to do is make sure that we know how to properly deal with these limits of integration here, being that they're written in terms of natural log. So now that we've discussed that, I'm going to go ahead and erase what I have here, and then we'll actually formally start the problem and see what our answer should be. All right, so for this problem here, I'll just go ahead and do it like this. We know that our antiderivative is essentially going to be 2e raised to the 1/2 x. And we're going to evaluate that from natural log of 9 to natural log of 25. Okay. So in doing this, we can ignore the 2. So we'll put that out for right now. And we'll have e raised to the 1/2 times 25 here minus e raised to the 1/2 natural log. Oh, so that's natural log, sorry. Forgot about that. So let me rewrite that over again. So this will be 1/2 times natural log of 25 minus e raised to the 1/2 natural log of 9. All right. So in looking at this, please note that here, if we use our exponential rules, we could rewrite this situation as follows. So we can say e raised to the natural log of 25, and we take all of that raised to the 1/2 minus e raised to the natural log of 9, all that raised to the 1/2. And so if you remember this log property here, we know that a raised to the log base a of x is x. And if you allow your a's to be the irrational number e, and know that log base e is natural log, then what we essentially have here is e raised to the natural log of x is equal to x. So here we know that e raised to the natural log of 25 is just going to be 25. Okay? And e raised to the natural log of 9 will just be 9. Now we also know here that 25 raised to the 1/2 is just the same thing as square root of 25. And of course, 9 raised to the 1/2 is just square root of 9. And of course, from here we know square root of 25 is 5, square root of 9 is 3, and 5 minus 3 is 2. So our final answer here just ends up being the value 4. So that will be my final answer for this example. And again, the point of this is to make sure that you're very fluent with dealing with log and exponentials as far as their logarithmic properties, exponential rules, because that comes out to be a handy thing whenever we're dealing with these integrals like what we're dealing with here. All right, so let's move on to our next example. So for our next example here, we see that we are dealing with a definite integral again. So we're actually going to get some real number value for our answer, because we're essentially trying to find the area under the curve of this particular function, 4 raised to the negative theta, from 1 to 2. Now, one of the things that we want to recall here is that since we are dealing with this exponential, if you remember that in general, if we take the derivative of, let's say, a raised to the theta, and I'll use prime notation here, if we take the derivative of this function here, then this will just be a raised to the theta times natural log of a. Okay. Now, if theta just so happens to be a function in and of itself, then of course we will use a chain rule, and we'll say d theta with respect to theta in this case, and that's why this ends up being 1. But let's say if this was something like theta squared, then we would be taking the derivative of theta squared with respect to theta. Okay, so my point here is that we know that if we were to take the derivative of a function like this, it would basically be proportional to itself, where that constant that we would have there is natural log of a. Well, if we did the antiderivative of this, then this would have to be same function but now divided by natural log of a. And we know that because if we reversed this process and figured out what is the derivative of a raised to the theta divided by constant natural log of a, we know that the derivative of a raised to the theta is just all this business here, and the natural log of a here and the natural log of a there would reduce to 1. So we keep that in mind. Now, if we were to add a minus sign onto this, then note that we could use the substitution rule, but this is kind of like the same situation that we had when we had e raised to the negative 1/2 x here, and we wanted to take the antiderivative of that. And we saw that if we did, it was just going to be the same thing, e raised to the negative 1/2 x, but now it would be divided by negative 1/2. Okay, so in that sense, we know here that if we have this, this would be a raised to the negative theta, and this would be a minus natural log of a. So we're going to take that and use this information to be able to figure out what the antiderivative of 4 raised to the minus theta is, and then evaluate that area on the curve from 1 to 2. So we're here and we say integral from 1 to 2 of 4 raised to the minus theta d theta. And that's just going to be 4 raised to the minus theta over a negative natural log of 4. And that will be evaluated from 1 to 2. And so in looking at that, first thing that we could do is go ahead and factor out the negative 1 divided by natural log of 4. And we'll just look at 4 raised to the minus theta. We'll look at that from 1 to 2. And try to make that natural log look a little better there. All right, so we have negative 1 divided by natural log of 4. And of course, if we plug in a 2 here, we'll get 4 raised to the negative 2 minus 4 raised to the negative 1. And of course, from here, this is just a matter of rearranging and making this look nice. So we will rewrite this. And 4 raised to the negative 2 is just the same as 1 over 16. And 4 raised to the negative 1 is the same as 1/4. And we'll go ahead and make our fractions have like denominators. So we do that. And here we'll multiply the numerator and denominator of our second fraction by 4 to make it like denominators. So we have negative 1 over natural log of 4. And then this will be 1 minus 4 over 16. And this will end up being, of course, negative 3 here. And negative 3 times a negative 1 gives us a positive 3. And then this is 16 times natural log of 4. And so we could leave this answer this way. Or if we wanted to, we could rewrite this as 3 divided by natural log of 4 raised to the 16 if we wanted to. Really doesn't matter. Either one of these answers is correct. We could also, just as another alternative way of doing it, let's say here we wanted to rewrite 4 as 2 raised to the 2. So if I did that here, then of course I could take this 2 and pull it out. And this will be 3 over 32 times natural log of 2. That's another way that we could express that answer. And so all 3 ways are correct. So just a matter of how you want to express it and how you plan on using the answer once you get it. Okay, let's move on to the next example. All right, so now we're back to doing definite integrals. And so in looking at this integrand here, we see that our innermost inside function is x squared. And if I took the derivative of x squared, I would get 2x. And of course, this x is the part that I'm worried about because I see that I have an x that I can recover in the remaining part of the integrand. So this lets me know I want to use a substitution rule. Okay. So here we're going to say let u equal x squared. And that implies here that du over dx is just going to be 2x, which further implies here that we can rewrite this equation as 1/2 du, and that would be equal to x times dx. And that's pretty much what we want because we want this x and this dx to be covered. So all of that would be replaced with 1/2 du. And of course, x squared here will be replaced with u. Now, since we have limits of integration here, one of the things that we can do is go ahead and translate these numbers that are in terms of x. We can translate them in terms of u now. so that way we don't have to worry about back substituting later to actually figure out what our answer is. So here we'll say also, we know that u of 1, because again, 1 is the lower limit, will be the same as 1 squared, which is 1. And we also know that u of square root of 3. Let's try to make that look better. U of square root of 3, it's just going to be square root of 3 squared, which would just be 3. So now that we have this all together here, we know that the integral of 1 to square root of 3 of x times 4 raised to the x squared dx, this is the same as the integral from 1 to 3 of, and of course the x dx, that's just going to be 1/2 du. And then we multiply that times 4 raised to the u. Okay. All right, so we have that. So now all we have to do is take the antiderivative of 4 raised to the u, because again, we'll ignore this 1/2 that's out here. And of course, the antiderivative of 4 raised to the u is just going to be 4 raised to the u divided by natural log of 4. And that will be evaluated from 1 to 3. And so pulling this over here to finish up, we know we have a 1/2. And I'm also going to go ahead and factor out that natural log of 4. And what we have here is 4 raised to the 3 minus 4 raised to the 1. And 4 raised to the 3, that will be 64. 4 raised to the 1, that will just be 4. And all of that will be divided by 2 times natural log of 4. Okay. And so in looking at that, we have 60 divided by 2 times natural log of 4. And of course, 60 divided by 2, that will reduce to 30. So we have 30 divided by natural log of 4. And if we wanted to simplify some more, we know that 4 can be written as 2 squared. And that will allow me to take this 2 and pull it out. So it'll be 30 divided by 2 times natural log of 2. And then that 30 and the 2 here will just end up being 15. So we'll have 15 divided by natural log of 2. And so our final answer here will just be 15 divided by natural log of 2. So that'll be our final most simplified type of answer. All right, so let's look at our next example. All right, so in this example, of course, now we have a logarithm, something other than base 10 or base e that's in it, and we want to take the antiderivative of that. We also see that the logarithm actually has a function stuffed inside of it, so this prompts us to want to try to do the substitution rule to see if that would work. Okay, so that's what we're going to try here. So we'll start off by saying, let u equal x plus 64. And of course, if I took the derivative of u with respect to x, that's just going to be 1, because the derivative of 1x is just 1, and the derivative of any constant is 0. So basically that lets me know here that du is equal to dx. So we also know here that if we want to translate our limits of integration from being in terms of x to being in terms of u, then we can say u of 0 is going to be 0 plus 64, which is 64. And u of 64 is going to be 64 plus 64, which is 128. So because of that, now what we have is that this integral from 0 to 64 of all this business here is actually the integral, or can be rewritten as the integral from 64 to 128 of log base 32 of u divided by u, and then du, because du is equal to dx. Okay. Now, this looks like we haven't really done anything special here, but this form here allows us to see a few things. One, if we were able to figure out what the antiderivative of this was straight up, the fact that we've changed over our limits of integration would allow us not to have to do any back substitution. The next thing that we need to realize is that log base 32 of u can be rewritten. And it can be rewritten in a way that will allow us to be able to figure out what the antiderivative of this particular integrand is easily. Okay, so note here that we have the change of base rule. The change of base rule says if we have log base a of say of b, I'll write it like that. If we want to change from one base to another, so I'm just going to put an X there because this will make this easier. And so let's say I want to change from base A to base B. Okay, so here this would be log of base B of X over log of base B of A. Okay, and so the point here is that whatever this is goes on top, whatever that base is here goes on bottom, and the log base B remains the same. So because of that, what that tells me here is that log base 32 of u, if I wanted to rewrite this in terms of a natural logarithm, this would just be natural log of u over natural log of 32. Okay, and so if I did that, then I could rewrite what my integrand is, and I would see that that actually makes it a whole lot easier for me to take the antiderivative. So here I am going to kind of do like this to continue on here. So we got integral 64 to 128, and instead of writing log base 32 of u, I'm going to rewrite it as natural log of u over natural log of 32. Okay, so we'll do the implied 1 divided by u here times natural log of u divided by natural log of 32. And that will be du there. All right, so now that we have this in this form, what we can do now is just basically factor out this 1 divided by natural log of 32. So if we do that, and then we write the rest here, then we'll see that what we essentially have on the inside is just natural log of u divided by u du. And again, we know how to deal with this. So we know that if we let natural log of u be some other variable, then the derivative of that will just be 1 over u. And of course, from there, we know that substitution rule can be used. Okay. So I'll switch colors again here. And we'll say, let W this time equal natural log of U. And if that's the case, then dW is just going to equal 1 over U times du. Okay. So normally I would actually, do this step here and then move it over, but we kind of already know what we're expecting here. So I'm just skipping a step there. All right. So once that's done, again, since we have now this new variable W, we can translate our numbers that are in terms of U into W now. So here, let's also look at this and say U of 64 is going to be the same as natural log of 64. And note here that 64 is just the same thing as 4 raised to the 3. So we could rewrite this as natural log of 4 raised to the 3, which would just be 3 times natural log of 4. Okay. We also have here that U of 128. Actually, you know what? We could rewrite that a different way. And I'm actually going to erase this and make this a little shorter here. So, yeah, sorry about that. And I thought about it. I was like, well, we can even write this in a more simple way. And this will prevent us from having to do work later. So I'm just going to go ahead and do it like this. All right, so we'll say here also, we'll say U of 64. And remember here that 64 is the same thing as 2 raised to the 6. Okay, so like 2 multiplied times itself 6 times gives us 64. So here we could rewrite this as natural log of 2 raised to the 6, which can be rewritten as 6 times natural log of 2. Okay. Now, we see that 128, that's just 2 times 64. So that will be U of 2 raised to the 7. And that would just be natural log of 2 raised to the 7, which is 7 times natural log of 2. So we have a different way of writing those limits of integration there. So therefore, we have what we were originally dealing with here. Seems like whenever I write too fast, it does that. So if I do that, then this is the same as, in this case, on the low end, we have 6 times natural log of 2. On the high end, we have 7 times natural log of 2. And here, this would just be 1 over U, or sorry, we need to do the substitution here. So we know that natural log of U would just be W. Let's get rid of, smooth this. Let's try to erase. Yeah, there we go. So natural log of U is W. And of course, this 1 divided by U du, that is dW. And of course, from here now, if we take the antiderivative of W with respect to W, that's just going to be 1/2 W squared. And we will evaluate the W squared part using these natural logs that we have here. And from there, we'll just continue to work on it and work it out. So I'll drop down here to finish up. So this is 1/2. And of course, we'll do, and I'm actually I'm going to rewrite this as natural log of 2 raised to the 7 here. No, okay, I think, yeah, we could leave it the way that I had it. So I'll pause this and keep it the way that it was, and then we'll finish up. All right, so we'll have 7 times natural log of 2. That will be squared minus 6 times natural log of 2, and that will be squared. That will essentially just give us 49 natural log of 2 squared, so like this, and then minus 36 natural log of 2 squared that. All right, so here there's, I think I lost this natural log of 32, so I'm going to go ahead and write that in here, because I forgot to write that down, and so that's kind of getting lost in the sauce here. So we'll say therefore, and this is 1 over natural log of 32. And so we'll just put this over here like that. And instead of this 1/2 here, what we'll do this is 1 over 2 times natural log of 32. Okay. All right, so this is starting to make a little bit more sense now. So I was like, yep, there's something that's missing. And so now, again, we have this 1 divided by 2 times natural log of 32. Okay. And at this point, I'm going to keep this 1/2 out here. But if I come here, notice that this natural log of 32, I could actually rewrite this as natural log of 2 raised to the 5. Okay. And if I did that, then of course, what I also understand is that that 5 that's in the exponent there can be pulled out in front. So here I know that I could rewrite what I have here in the denominator, that natural log of 32 is really just 5 times natural log of 2. Okay. All right, and so now that I have that, notice here that your numerator has natural log of 2 squareds in them, and we have a natural log of 2 in the denominator, so we can actually factor that out. So I have a natural log of 2, I can factor out there. And this is a 2 times 5 times natural log of 2. And then from there, we'll just have 49 times natural log of 2 left on the inside, minus 36 natural log of 2 left on the inside here. And these natural log of 2s will reduce to 1. I'll just have 1 over 10 here. And if we take 49 natural log of 2s minus 36 natural log of 2s, I got 13 natural log of 2s left. And so this would just be 13 over 10 natural log of 2. And that would be my final answer for that one. All right, so with this problem, this concludes our examples for going over integration involving exponentials and logarithms. And I hope this video was helpful to kind of help you to be able to navigate with these kind of integrals that we deal with sometimes. And again, hope it was helpful. Take care.